Okay, good morning, everyone, and thank you for joining our final press conference, or press briefing of the AGU fall meeting. I'm Becca from the AGU Media Relations Office, and along with my colleague Hope, I'll be helping moderate this press briefing. Our final press event of the conference is coming to us from NASA, the latest science from the biggest story in the solar system, NASA's Juno mission to Jupiter. We will begin with each of the panelists giving brief presentations describing their work, and then we'll open it up to questions from reporters. We will end on the hour or when there are no more questions, whichever comes first. Reporters, because this is a Zoom webinar, you won't be able to turn on your video or microphone without being invited to do so. So if you would like to ask a question, please type your full name and affiliation into the Q&A box, not the chat box, but the Q&A box. And we will request that you unmute yourself and you can then ask your question. Alternatively, in addition to typing your full name and affiliation, you can type your full question and Hope will pose it to the panelists on your behalf. And we will respond to questions or call on you to ask your question in the order in which they're received in the Q&A box. You can write in your question at any time, but we won't respond to them or ask it until the panelists have completed their presentations and we are in the Q&A portion of the Reporters, please also make sure that your Zoom name is accurate so that we can easily find you in the participant list. Slides and additional materials from this briefing will be posted to the Press Information Exchange on AGU Connect, and we'll drop a link to that in the chat. This press briefing is also being recorded, and the recording will be posted to AGU's YouTube channel, as well as shared on the Press Information Exchange. Please bear with us should any technical issues arise. If Zoom webinar goes down for some reason, we will switch to presenting this press briefing through a teleconference line. And if we do that, I will immediately send out an email to all panelists and attendees with information on how to access that teleconference line. Otherwise, if you experience any technical issues during this press briefing, please email news@agu.org and we'll do our best to get you set up. And with that, I will now turn it over to our panelists today.
Okay, hi, I'm Scott Bolton, the Juno principal investigator, and we call this the biggest story in the solar system because Jupiter is the largest of all the planets in our solar system. It's more than 10 times the size of Earth, and in fact, it's so large, all the other planets, comets, asteroids, everything could fit inside. There'd still be room to spare. And we're going to give you kind of a quick overview. I'm really excited to share with you our latest results. I'll give you a quick sneak preview of some of the results that we got when we flew by Ganymede back in June, and then some of the latest images and science that we've obtained just about 2 weeks ago on our 38th close flyby of Jupiter. We're in an elliptical orbit. We used to go by about every 53 days. And now it changes a little because the satellites are moving us around. We're going by the Galileo moons. And that's why I'm going to show you some results from Ganymede. And then we'll go on and there'll be a couple of other speakers. The next speaker will be Leah Siegelman, and she's actually from France. She's working at or speaking to us from France, but she's part of Scripps at UC San Diego. And she's not a complete member of our team, but actually was looking and studying the ocean. She's an oceanographer and noticed a similarity between Earth's oceans and Jupiter's beautiful atmospheric dynamics. And so she'll be showing us how similar and the differences between them and how you can learn from studying both the ocean at Earth as well as Jupiter. And then staying with that theme of comparing Jupiter and Earth, Jack Connerney will be the next speaker. He's our deputy principal investigator, but also the lead of the magnetometer. And on the 34th pass just this summer, we completed our complete map of the magnetic field, and Jack will be talking about the results once we've got this whole map of Jupiter's magnetic field and comparing that to Earth's magnetic field and what we can learn about one of the features that we discovered there called the Great Blue Spot, not to be confused with the Great Red Spot, but this is a magnetic feature, but looks a little bit similar, and he'll compare the two and talk about how fascinating it is and what we can learn from studying that. And then finally, the last speaker is Heidi Becker. She is our co-investigator that leads the Stellar Reference Unit, which is a star tracker. It's actually how we navigate around Jupiter. We study the stars, we figure out where they are and figure out their position. But she's using that instrument as a science instrument. And what she's going to report on are some very unique images that we took of Jupiter's rings, and looking from the inside, looking out, a perspective that only Juno can actually provide. And so let me jump right into some of our first results from this summer when we flew by Ganymede. Could I have the next slide, please? So this is a picture, an image that we took with the JunoCam instrument, and it was created by one of our citizen scientists named Bjorn Johnson. And we released an image similar to this right after we flew by, but it wasn't nearly as processed. And this one really shows a lot of the detail. What you can see in this image are the both dark and medium gray terrains of Ganymede that make up its geology, and then these bright splash, the bright splash thing that you see on the right side, that's actually called the Tross crater. It's one of the most outstanding and beautiful features on Ganymede, and what you're seeing is a crater created by an impact, and that because Ganymede's covered in ice, it scatters up the ice and almost like snow and makes this really bright feature. The dark terrain that you see on the left side, kind of scattered around the lighter gray, that's thought to be some of the older terrain of Ganymede. And of course, our observations, we used a full payload of Juno to study Ganymede, and some of those results are being presented here at the AGU. They're very preliminary. We're still trying to figure out what we saw and what it really means, and that'll come at a later press conference, but I wanted to share this. You can even see not only the craters, but some of these linear features, almost straight lines like features in the light gray areas. Those are believed to be coming from tectonic activity. These were all kind of known. This particular image was taken at a distance of about 645 miles away from Ganymede that we flew by in June. And the resolution's about 1 kilometer. So we have similar resolution from some of the best images of Ganymede from Voyager back decades ago. But this is kind of a new view for us. And there's a lot of science in this, and it's just fantastic image. The next slide, please. And so here, what I'm going to show is actually something that we observed with our WAVES instrument. This is sort of, we're flying a radio going by Jupiter, going by Ganymede, and you're listening. We take that WAVES instrument that measures plasma waves and radio emission, and we convert it down into the audio range. And so you're hearing this. And if you flew a radio, which is really what we do when you fly by Ganymede, this is what you would hear. And you hear the main frequencies that you're hearing as they rise up are basically attributed to the electron density. When a scientist looks at a picture like this, where you see a rise in that frequency, electron density, and then a drop, you know right away you're going through a magnetosphere. And of course, Ganymede is the only body that we found, only moon in the whole solar system that we found that actually has its own magnetic field and its own magnetosphere. And inside that magnetosphere, it's like a bubble inside of Jupiter's magnetosphere, and inside that bubble is filled with charged particles that Ganymede sort of supplies. And of course, outside of that bubble is Jupiter's magnetosphere, filled with Jupiter's plasma and charged particles. And outside of Jupiter is the sun's heliosphere. And so you're seeing a bubble inside of a bubble inside of a bubble. And what's amazing about this, and we saw something similar to this with Galileo when we flew by Ganymede, and in fact, that really led us to kind of take a look at Ganymede, because we knew it was very special. We had never seen a moon that had this signature before, and we knew that it probably had its own magnetosphere, and we started searching and found that it had a magnetic field. So this is the Juno version of what it sounds like to fly by Ganymede. Next slide. And so here we also took the images that we got from Ganymede. We took 4 images altogether of of Ganymede, and we composed some music with a composer named Vangelis. And this is actually going to take you on a ride as if you were on Juno. What would it be like to fly by Ganymede? So we approach from the dark side. You can see this is all sort of true to form of our trajectory roughly. The sun was lit that way. And we fly over Ganymede, and you see these incredibly beautiful craters, these linear features that I mentioned, the dark and the lighter terrain, and then where each of these impacts have stirred up for sort of fresh ice. And you remember, you're flying over at a distance of only about 600 miles. And then as we fly past Ganymede, you'll see it sort of go into the distance. And then the spacecraft turned its attention onto Jupiter. And so again, we approach Jupiter a little bit from the dark side, coming over the northern pole of Jupiter, and you'll see that come into view in just a moment. At the closest approach to Jupiter, actually, you're closer to about 5,000 kilometers above, but we're just coming over the pole here. It took 16 hours to travel almost 1 million miles or so that Ganymede is away from Jupiter. So we're moving at a pretty fast clip. And you see we come in on the night side, and all you can see is some lightning. The lightning we aren't measuring with this with the Juno Cam images that I'm showing you. We measure lightning with other instruments. In fact, one of the instruments we measured it with was the SRU that Heidi will talk about later. But Juno Cam can see it on the night side, and we have the plasma wave instrument that I played the sounds from flying by Ganymede also is able to measure lightning. And finally, our microwave radiometer measures lightning. So we have a lot of ways to measure lightning, and we can learn where they're coming from. And they're coming from these big storms. And so we put flashes in where we see lightning occurring through other instruments. They're not actually embedded in this, but these are the real images of Jupiter that are processed into a moving animation by just putting them together. And you can see that how incredibly beautiful Jupiter is. It's really an artist's palette. This is almost like a Van Gogh painting. You see these incredible vortices and swirling clouds of different colors. And in fact, it's these kind of images that really motivated and inspired Leah, our next speaker, to take a look at it and say, wow, because these looked a little bit like what she was studying in Earth's oceans. You can see that we got really close to Jupiter as we passed over the low latitudes. And then we come out the South Pole, and you see sort of this string of pearls, which are individual Jupiter vortices, giant white storms. And we go out the South Pole, and you can see at the pole just the beginning, sort of half lit, of the giant polar cyclones that exist at both of Jupiter's poles that are shaped in like a polygon. And in fact, Leah will talk a little bit about that as well. So this is really to give you a starship captain view. If you were lucky enough to fly on to Juno and go to Jupiter, you would experience an incredible Disney-like trip as we fly by these alien planets and moons that are in our solar system. So we wanted to share that with you. Next slide, I'm going to just show a couple of, so here is an image that we took quite some time ago, and we actually showed it before. This is a picture of Europa from a distance of about 80,000. And this is what's new about this is that you're seeing the northern polar region, which hasn't been imaged very well. And what I wanted to do was kind of capture the idea that in our extended mission, one of the things that's new with Juno is we're going to go close by each of the satellites. So we did Ganymede, and I just showed you some of the results from that. Europa will fly by next fall, really close at a distance of only about 360 kilometers or so. And this is a long shot distance, but it is another Galilean moon. And we're really excited to be able to expand Juno science into the moons and rings of Jupiter, while the primary mission was focused on Jupiter itself and its aurora and magnetosphere. Next slide, please. And so here's another shot that just sort of closes up all of the Galilean moons. So this is a beautiful image of Jupiter. that we took at a distance of about 6,000 not sure, right? Brian Swift took this thing, but I think we were pretty far away actually. Brian Swift made this image. She's another one of our citizen scientists. And what's unique about it is you're looking kind of at the northern region, but you actually capture Io and Callisto. And you can see in the inset, the bigger lit one is Io. And then just to the right and a little bit lower is Callisto. So between this image where you have Io and Callisto and the Europa image I just showed and Ganymede, that's all 4 of Jupiter's Galilean moons. We'll fly by close by 3 of these. We already did Ganymede. Europa's next fall, and a year or so later than that, we'll do Io, and we'll actually fly by Io twice really close at a distance of 1,500 kilometers. Io is the most volcanic body in the entire solar system. So each moon has a unique kind of science interest to it, and we're very excited to be able to study all 3. Next image. And so this is one of the most beautiful images that we just got from our flyby that just happened 2 weeks ago, the 38th flyby of Jupiter, really close up. And what you see in here are 2 incredible examples of how beautiful Jupiter's vortices and vortex storms really are. And there's a difference in the shape. You see one that's much rounder and the other one is elongated. Both show these, what we call pop-up clouds. We believe a lot of lightning, and these are the storms. These are rising clouds coming out of Jupiter on strong updrafts, maybe ammonia. You can actually see some shadows in these. These are some of the best examples of these pop-up clouds. And while this image was about 6,000 kilometers away Jupiter was about 6,000 kilometers away from Juno when we took this image, and you're looking at about 50 degrees northern latitude. And those pop-up clouds look small. The resolution of this image is about 4 kilometers, so it's pretty high resolution. And those pop-up clouds are 50 kilometers across, some of them on the average. And so even though they look tiny in this, they're very big, especially when we think about, Earth scale. Okay, well, with that, I'd like to introduce Leah, who's going to actually talk about some of the aspects of these beautiful vortices and how they compare to Earth's oceans. So Leah, take it away.
Thanks, Scott. So yeah, as Scott said, I'm a physical oceanographer at Scripps Institution of Oceanography at the University of San Diego. And I wasn't originally part of the Juno mission, but I got really interested by it a few years ago as a graduate student. I saw the first images of Jupiter's North Pole taken by the Juno mission. And especially, it reminded me of the oceans, the turbulent ocean that I was studying at the time around Antarctica. And so today, I'd like to show you how, using my background as a physical oceanographer, I was lucky enough to study Jupiter's atmosphere, and in turn, how that can help us to understand our own planet better. So on the next slide, what I'm showing here is a satellite image of Earth's ocean. It's taken here on the right. There's an inset that shows you where it's taken. It's between the coast of Sweden and Finland. And on the left, you can see the coast of Sweden. But really what you're seeing here is phytoplankton. So chlorophyll that's created by phytoplankton, and this really gives you the signature of the ocean currents. And you can see here how it's the ocean is very turbulent, and there's a lot of small eddies and filaments and meandering front, a little bit like the images that we were seeing before. And so on the next slide, I'm going to show you a zoom of this one. On the left one, so on the Baltic Sea, so this is a zoom of the previous image, and on the right side, it's a turbulent cloud on Jupiter. And I hope that you can see, just as I saw, how strikingly similar those 2 images are, and really how the underlying dynamics and the turbulence is the same. And just to convince you a bit more of that, we're going to look on the next slide is an animation that shows a morph. So here we start with this image, in the Norwegian Sea of a structure, that typical structure that's called a dipole. It's made of a cyclone and an anticyclone. This one is in the ocean. Again, it's chlorophyll, and slowly it's morphing into one of those dipole structures that we can see in Jupiter's turbulent atmosphere. So here, this here is actually a vortex dipole in Jupiter's atmosphere. And it's really, even though the scales are completely different, like in the ocean, though the vortex in Jupiter are around 10 times bigger than those in the ocean, we can clearly see that they're generated by the same sort of dynamics. And so in the next slide, you're seeing those two images close to each other. So the vortices in the ocean, in the Norwegian Sea, and those in Jupiter's turbulent atmosphere. So that really showed me how strikingly similar those two were. And so if we can get the next slide, please. So yeah, then I will try to understand a bit more the formation of the vortices that we see at Jupiter's North Pole, the famous polar vortex crystal. So here now is an image taken by the GERM instrument on board Juno. It's in the infrared band, and you can see this is the North Pole with the circumpolar cyclone that are organized geometrically around a polar vortex. And this structure is very intriguing, especially because we can find it in nature. Like, can I get the next slide, please? So on the next slide, I show on the left, it's the south pole of Jupiter this time, where you can see one big polar cyclone surrounded by 6 circumpolar cyclones. And on the right side, it's a plasma physics experiment. So completely different scale, but you can see that the electrons also spontaneously organize in sort of crystal. And so this was really intriguing, like how come those patterns naturally emerge in nature? And so with my team, we formed a simplified model of a pole, and this is what I'm gonna show you in the next slide. So what we're going to be looking at is just the pole of Jupiter, and in red, it's going to be the motion, the cyclonic motion, and in blue, the anticyclonic motions. And we're going to see, first, we've seen here the 6 first months where it's quite turbulent, and slowly the turbulence organizes itself. And it goes to this natural vortex crystal form. And here we're seeing the last 6 months of the simulation, where the vortex crystal is stable and well established and just survives forever. And this is very reminiscent of what Juno was able to observe at the pole of Jupiter. And so it suggests that the just basic configuration of the planet allows the formation of such geometric pattern. So yeah, with that, I'm just going to conclude my talk and say that I felt very lucky as an oceanographer to be able to study the atmosphere of Jupiter, and that I'm hopeful that in the future what I've learned will be useful for my ocean studies, and maybe one day, who knows, I'll be able to study the oceans on Europa thanks to the extended mission of Juno. And with that, I'll give the talk to the next speaker, Jack Connerney, who's going to tell us about another way that Jupiter is similar to Earth, and is going to talk about Jupiter's magnetosphere.
Yes, as Scott said, I lead the magnetometer investigation, and I think we do truly have a very large story for you today about the magnetic field. Before we move on, I want to point out that our instruments are hosted at the outer edge of the solar panel, that appendage you see on one of the solar panels. Now, how do we measure the magnetic field? If I can have the next slide, I'll show you how we put together our orbit segments to map the magnetic field very accurately. And Juno is the first polar orbiter we've had about Jupiter. And so we're really the first spacecraft that has an opportunity to map the field globally. Now, Juno's orbit is a very large orbit. We come in from the far reaches of the magnetosphere during the prime mission just about every 53 days. And we pass very close to the planet, race over the cloud tops, and we create our data set with about a 2-hour segment every 53 days as we pass close to the planet. And we time those orbits so that we sample longitudes in a very deliberate fashion. And so the outcome of that is what you see on the screen here. We put these 32 orbits from the prime mission together and modeled the magnetic field. And I'm going to show you in a minute what that looks like. Of course, we can't see magnetic field lines, and so we have to use a different kind of graphical representation, and that's shown on the next slide. On the top, we have a rendition of the magnetic field model we've developed for Jupiter. Now, what you need to know is that the field lines come out of the planet where it's yellow and red, and they go down into the planet where the colors are blue. And then the darker the color, the more closely packed together the field lines are when they emerge from and sink into the planet. Now, one of the remarkable things about this plot is that it's extraordinarily unlike the magnetic field of the Earth. The positive field lines are emerging from a band at mid-latitudes, you see in the red. And there's a very peculiar feature, an anomaly, this blue spot at about 90 degrees longitude. That showed up early in our mission, and we've been eager to learn more about it ever since. And just for comparison, beneath this contour map of the magnetic field is what we knew about Jupiter before Juno. And you can see that while there's some resemblance in a very vague, sort of ambiguous way, it's really not possible to interpret the lower figure in terms of what's going on inside Jupiter. And that was a result of our flybys of Pioneer 10 and 11, Voyager 1 and 2, and Ulysses, and the orbiter Galileo over the past 4 decades or so. So we've made tremendous progress with Juno as a result of our mission plan. So before I get into what we've learned, we need to look at the interior of Jupiter. So if we can have the next slide. This is a pie chart that shows you how we think Jupiter is constructed on the interior. And it's compared on the lower right with a pie chart for Earth. And of course, the first thing you notice is that we don't call this the gas giant for nothing. It's about 300 times more massive than the Earth, and it's over 1,000 times larger than the Earth in volume. So it truly is a giant planet. And it's mostly hydrogen, a little bit of helium, and then a sprinkling of heavier elements. On the outermost part of the planet, the hydrogen is in molecular form and convecting. At the very top of that layer, you see the visible atmosphere. As you go deeper, the pressure and temperature is such that the electrons are squeezed off of the hydrogen atoms, and it becomes metallic, becomes a good electrical conductor. Those little symbols show you where we believe the interior is convecting. And of course, in order to have a dynamo, in order to power a magnetic field, you need an electrical conductor, and you need it to be in motion. It has to be convecting. Now, most models have an odd layer, stably stratified layer at the very top of the metallic hydrogen, where the helium expresses out of the metallic hydrogen. It's an immiscible, that like oil and water, it doesn't mix. And so the helium forms droplets. And because helium on Jupiter is heavier than air, hydrogen, it sinks towards the bottom. So let's look at Earth now for comparison, because what we're going to use what we know about Earth to interpret what we've learned at Jupiter. So the Earth's interior is quite different. Of course, Earth is a rocky planet. We live on that very thin crust at the top. That's about 1% of the Earth's interior. Beneath that is a rocky mantle. And then at about half the planet's radius is the core. The core has 2 parts. The outer core is a fluid, iron, convecting. That's what powers the dynamo, the magnetic field on Earth. And the very innermost part, the iron has solidified into a solid inner core. But we know from seismology, and that's the science of sending sound waves through the Earth, we know that the outer core extends to about half the planet's radius. But we also know that just by looking at the magnetic field. If I can have the next slide. This is a plot called the Lowe's plot, and it organizes contributions to the magnetic field based on the scale size, if you will, of that contribution. So large scale sizes are on the left of the plot. And as you go to the right, scale size of that contribution gets smaller and smaller. So look at the plot for Earth. On the Earth, those data points, the filled data points, they are organized by a linear fit. It's called the Lowe's radius, which identifies the surface of the dynamo at 0.54 Earth radius. The unfilled symbols off to the right at small spatial scales, that's due to the crustal field on Earth. That's due to the rocks beneath our feet, permanent and induced magnetization in the rocks that are in the iron-bearing rocks in the Earth's crust. And that is an obscuring haze, really, beneath which you cannot really view what's happening deep into the Earth and the dynamo. So if you look now in the upper part of the plot, that's, say, the same kind of a representation for Jupiter's field. First, you notice Jupiter's field is 20,000 times stronger than the Earth's field, but it organizes with spatial scale in a very similar way to the Earth. And the Lowe's radius fit for Jupiter is at 0.81 Jovian radii. So if we are to learn from the Earth how to identify the dynamo core surface, on Jupiter, that places the dynamo core surface just beneath the layer stabilized by helium rain in convecting metallic hydrogen. So that settles a sort of a long-standing question as to where Jupiter's field is generated. If you accept this argument, we know where it is now. If I can have the next slide, let's get back to that great blue spot that Scott mentioned. This is an orthographic projection of the field from a vantage point looking down upon the great blue spot. Superimposed on that projection, we have the measured surface winds, the zonal winds. These are east-west trending winds that are measured simply by tracking features at the cloud top level. So you track them over many, many days and years, and you can precisely determine how fast they are moving east or west with regard to the solid body rotation of the planet. So as you can see, the great red spot sits in a region where winds are moving eastward at about 100 meters per second. But just beneath the great blue spot, at the southern extent of the great blue spot, the winds are moving westward. And above the great blue spot, just north of the great blue spot, the winds are moving eastward. And you can see the contours of the great blue spot mysteriously are extended in the same direction as the zonal winds, both below the spot and above the spot. And we believe this indicates that the great blue spot itself, the magnetic field, is being torn apart by these zonal winds that penetrate deep into the planet. And we know that they have to penetrate at least about 3,500 kilometers into the planet in order for the electrical conductivity to grow large enough to grip field lines and pull them east and west. So that's kind of a remarkable result. It's consistent with the analysis that our colleagues in the gravity investigations have been doing. And it poses the question, what about the great blue spot itself? So one thing we did, if I can have the next slide, is we tried to see if we could detect a difference in the magnetic field over the few years between the beginning of the mission and now the end of the 32 orbits. So this is a representation, a contour plot of the radiomagnetic field, the difference in the radiomagnetic field over the 2 years or so difference in our epochs, model epochs. We looked at the field beginning in the first 8 orbits, and now we're looking at the field over 32 orbits, and we're asking the question, what's the difference? So very clearly, we see that there is a significant difference, and it's associated with these 2 features on either side of the great blue spot at 90 degrees. If you take that great blue spot and drift it to the east, you get an increase in the negative field, the blue to the east of the great blue spot, and you get a positive contribution to the west of the great blue spot. And in fact, when modeling this, we find that we can account for the change in the magnetic field observed over the 5 years in orbit by simply allowing the great blue spot to move eastward at a rate of about 4 centimeters per second. And it's moving in the same direction as indicated by the zonal winds measured on the surface. So that is truly a remarkable result. And it's similar to what we know of the Great Red Spot. The Great Red Spot, of course, is the atmospheric storm at 20 degrees south latitude. And we know that that moves westward in the same direction as the zonal winds measured on the surface, but it moves at a rapid clip relative to the Great Blue Spot. It's moving at about 4 meters per second. And the Great Red Spot loops the planet every 4.5 years. The Great Blue Spot, the magnetic feature, in contrast, will take about 350 years to make one circuit around the planet. So we won't see it do that in our time, but we can continue to measure it. And in fact, during the extended mission, we're going to ever increase the resolution with which we can see the field, because we'll be putting orbits in between the orbits we already have in the bank. And that is going to increase the clarity with which we can view the dynamo down at the surface where it's generated. So it's truly an exciting prospect for the extended mission. And of course, we're looking forward to it. So that's all I have for the magnetic field. Now we're going to introduce Heidi Becker. She's going to show us what the rings look like from the inside out.
Thank you, Jack. As Scott mentioned, I'm the lead co-investigator for our Stellar Reference Unit, which we call the SRU. And it's actually an engineering camera that takes pictures of the stars to help us navigate Juno. But it's also an incredibly sensitive low light camera. And because of that, we've been using it to study very dim features and phenomena in the Jupiter system, like lightning flashes on Jupiter's dark side. And today we want to share a very special SRU image that we collected during our 36th close flyby to Jupiter on September 2nd, when Juno was only about 8,000 miles away from Jupiter's cloud tops. So if we could have the next slide, please. So what you're seeing here is an image of Jupiter's incredibly faint dust ring, as Jack said, collected from inside the ring, looking out. And this is a perspective that only Juno has ever had. And we can see an incredible amount of structure in this high resolution image. It's 32 kilometers per pixel resolution. And the two narrow, very bright bands and the more diffuse band that's just above it are all part of Jupiter's main ring. And Juno was about 30,000 miles away from the ring when this picture was taken. And the brightest thin dust bands and the neighboring dark regions that you see in between them are linked to two of Jupiter's very, very small moons, Metis and Adrastea. Metis is only 27 miles across, and its orbit is in the darker band that's just above the top bright band. And Adrastea is even tinier. It's only 10 miles across, and it orbits inside the dark band that's just below the bottom bright band. And these two moons are thought to sculpt those inner edges of the main ring. And they may, from collisions with other bodies that strike them, be the bodies that are contributing to the dust in the ring. But there's still an incredible amount of mystery about Jupiter's ring system. We don't really know its full structure, how it formed, or what all the sources of the dust are. It's believed that there are very tiny moons that are the source of the dust in the ring, but they've never been observed before. So it's really a very intriguing area, and scientists like studying rings because they're thought of as sort of little mini laboratories of how planets form that we have the advantage of watching as they're evolving and forming. The Juno team is very excited because as our extended mission orbit evolves, it's going to let the spacecraft fly deeper and deeper into the ring from the inside out, which has never been done before. And that will allow us to map the innermost dust population for the very first time. And we'll do that in kind of a unique way by detecting the impacts of the dust particles on the spacecraft and on the solar panels. And we'll also have the chance to take even higher resolutions of the ring with the SRU to study the very fine structure and the processes that might be causing it to form the way it does. And we hope we'll do that. But let's go to the next slide because there's something else going on in this picture. The SRU is, after all, a star tracker, and it's always got its eyes on the stars. And in this image, it also captured from this very unique vantage point on September 2nd, the arm of the constellation Perseus. And what you can see here above the dust, the diffuse part of the dust, is the star Algol. That's 93 light years away. And it's also called the demon star because it's an eclipsing variable star system, which means it's got a very dim star that passes in front of a very bright star every 3 days, which causes it to appear as though it's winking. So this forms the winking eye of Medusa's head in this constellation. We could have the next slide. Yes, we've added an engraving by an amateur astronomer who is named Johannes Hevelius, and he created this engraving over 300 years ago. And here you can see Perseus playfully dipping the head of Medusa into the dust of Jupiter's ring. And it's always so breathtaking that you can see a constellation that's familiar from a spacecraft that's orbiting Jupiter, and it looks pretty much the same as how it looks from our backyards here on Earth. And it's really just a humbling and awe-inspiring reminder of how small we are and how vast the universe is, and how incredibly much there is still left to explore. So we wanted to share this particular image with you all to herald in our extended mission and to share our excitement of all the opportunities that are in front of us. So thank you all for coming today.
Thank you to our panelists for sharing your work with us. We will now open it up to some questions from reporters. As a reminder, only registered reporters may ask questions. If you would like to ask a question, please type your full name and institution into the QA box, not the chat box, and we will invite you to unmute in the order of the questions that are received. If you would prefer to ask your questions without speaking, type your complete question along with your name and affiliation into the Q&A box. We will end the press briefing at 12 or when there are no more questions. Okay, our first question is from Leo at Irish TV.
Okay, thanks for doing this. Can you hear me okay? Ah, good, okay. I was wondering, I guess this is for Scott Bolton, the amazing imagery of Ganymede. One thing that struck me, I mean, I assume I should have noticed this before, but there seems to be something weird about what I would normally call the central peaks of the craters. They don't seem to be peaks at all. They seem to, many of them, be circular features at the center of the craters. And I was just struck by this and wondered if you might be able to explain that to me. And if I could, just as a general question, ask you, I had the pleasure of being at the Cape when Juno left Earth, and I'll be absolutely blunt with you. To my embarrassment, I really don't think at the time I fully appreciated the wealth of scientific data that was going to come back from this mission. I wonder, was that just me being a cynical old hack, or have you guys been impressed by the quality of the data that you're getting? And I do have a follow-up if there aren't many other questions. Thanks.
Okay, so let me take them in reverse order. We've been shocked pleasantly surprised by what we've discovered with Juno. And at the time of the launch, I mean, we knew we had high quality instruments and we were going into a very unique perspective. And so it wasn't so much the quality of data that surprised us. I think we all knew we had state-of-the-art instruments. The spacecraft was going into a place that had never really been visited, and we were going to see new things. I think what really surprised us in a nice way was how many ideas or notions that we had about how Jupiter worked that were sort of proven wrong, or there was so much more to the story. And you heard a little bit about it today, you know, with the magnetic field. I mean, we had no idea that the Great Blue Spot existed. And I could go on, and, you know, the interior structure of Jupiter, the existence of a dilute core, the atmospheric variability down deep, how the aurora works. I mean, all of it was shocking and surprising and quite honestly humbling, right? I mean, scientists like to believe that you're studying these bodies. We've sent other spacecraft to Jupiter and the outer planets with Voyager and Pioneer and Galileo and even Cassini. And so while you certainly hope to learn new things, and a lot of what you get are, you know, challenges, and you would sort of formulate your next questions from your previous mission's discoveries. I don't think anybody really expected that we would just be blown away in every field that we were studying. Even the discovery of the polar cyclones, right? Nobody anticipated anything like that at Jupiter's poles. We had never seen what Jupiter's poles look like because we can't see them from the Earth. Even with great telescopes like Hubble or James Webb, they can't see the pole of Jupiter because you got to get over it to be able to see it. And so when you go up close and personal to a giant planet like this, and you get a new perspective, I mean, it's sort of a lesson for space exploration that you are going to encounter brand new ideas, and you are going to modify your concepts of how things work. And Juno is a great example of that. And so then going on to your other question about Ganymede's craters, I'm not a geologist in expertise, but I can tell you that you know, craters have been studied for a long time. They often believe that, you know, you're seeing something that's a giant divot, and then there's an inner peak, and that's not totally uncommon. We see, you know, craters on our moon. We see them on the moons of Jupiter and on Saturn, and almost everywhere in the solar system we study craters. And in fact, they tend to count them, and they get an idea how old the terrain is, because something that's changing a lot can actually erase the crater record a little bit, and that gives you an idea. Now, with respect to Ganymede, we're still sort of sorting out that image and all the images that we took, and trying to learn about what that tells us about the craters. So it's a little bit too early for me to take a guess as to what we're going to learn, but I can tell you that the Tross crater, at least, and probably other ones, have some surprises in them that we, you know, are a little bit different than what we'd assumed. How that forms exactly, I think, is still going to have to be debated. You know, whether you see something that's a divot versus an elevated region, and what that's like, I mean, is all sort of work to be done. In the next couple of months, we hope to be able to delve into our results from Ganymede more and start to put together scientific papers. And we'll probably have a follow-on press conference at some point that's completely focused on what did we learn from Ganymede. So here you just got kind of a sneak preview and a little taste of it. And hopefully you enjoyed the little animation, so you could see what it was, how exciting it would be to fly by as an astronaut. So thanks for your question.
Okay, our next question is from Monica Young at Sky and Telescope. Can you say a bit more about the cause of the Great Blue Spot? I understand that the zonal winds are moving the spot eastward over time. Are they somehow also involved in its creation to begin with?
So I'm going to let Jack go for that one.
Yeah, so since the Great Blue Spot is a magnetic feature, it has to be created down deep in the planet. We think at about 0.8 planet radius where the dynamo operates. And it can be modified, though, at a much higher radius by the zonal winds. The molecular hydrogen that's in the very uppermost layer, that becomes more electrically conductive the deeper you go into the planet. And so we know you have to get down about 3,500 kilometers before the electrical conductivity is sufficient to be able to grip field lines and move them. Now, if it were a perfect conductor, you would then know the fluid flow. You could just see how the feature moves, and it wouldn't slip with respect to the fluid flow. So you could basically map the flow of fluids deep in the planet. But there's a complication. The complication is it's not a perfect conductor. And so while you're moving the field, it's also free to diffuse out through the conductor. So it's a more complicated problem. So you want to think of it as being a field like a sunspot, for example, generated deep inside in the interior and modified by a conductive flow at a much shallower depth, a few thousand kilometers. But it's going to be a long time before we model this in detail. This is going to be a treasure trove for dynamo theorists in particular, because now we have an example of a dynamo really for the first time where we can stay on target and we can see it with ever increasing clarity, much more than you could ever do in orbit about the Earth. So the dynamo theorists are going to score a trifecta on this one.
Thank you. Right now we have no more questions. I'm going to keep the Q&A box open for a few minutes. Leo, do you have another question?
Yeah, if I might, a couple of questions for Jack Connerney, if I may. The first is, I assume there's absolutely no, representation of this blue spot in the surface clouds. I'm assuming that's the case. That's my first question.
Yeah, we've seen nothing that we could identify with it because Jupiter is full of these cyclonic and anticyclonic features practically everywhere you look. So it would be a stretch to associate the Great Blue Spot with a surface feature in the clouds, for example.
Yeah, I kind of guessed that. Could I, a question still for Jack out of left field, could I ask you about zodiacal light? I know it's not in this briefing, but you published in the past year since the last AGU on this subject. And I'm just wondering if you could just summarize where you are with that, which, it was really quite a surprising finding for old fogies like me who thought they knew what they were seeing.
Oh, and it was equally surprising to many people in the field. I can tell you that based on the reviews we got. I don't want to hijack the press conference. If there are any other questions waiting for this subject matter, we should go to those. But if there are no questions, I could spend a minute describing the dust impact work and the zodiacal light.
We have one more question, but I think it might make sense to answer this now.
Okay. The dust story is another example of a serendipitous result. We didn't build a dust detector. We built star cameras to fly with a magnetometer. And we saw some confusing data in the imagery. And so my colleagues at the Technical University of Denmark looked into it in great detail, and we found that we could actually track with the star cameras, imaging 4 times a second, we could track pieces of the spacecraft ejecta that result from hypervelocity impact with tiny dust particles, micron in size, tens to 100 micron. And so we were able to use the spacecraft's 60 square meters of solar array as the world's largest dust detector ever flown in space. The dedicated instruments that have flown to detect dust have an aperture of about a square meter or less, 1/10 of a square meter. And so they don't see the particles in the size range we were looking at in great numbers. They see 1 or 2 a month. You can't learn anything from that. We saw about 250,000 impacts on the spacecraft during our transit from Earth to Jupiter. And that gave us an extraordinary amount of detail into where the dust is coming from and how it behaves dynamically, how it scatters into a cloud that in fact reproduces the latitudinal variation in the zodiacal light, which was a real surprise to us. So the moral of the story is, if you see something you don't understand, just keep digging on it, because there's likely a kernel of very important information that you can glean from it.
Okay, our next question is another follow-up from Monica Young, and this is a follow-up to the Great Blue Spot question. Why can you observe Jupiter's magnetic dynamo better than Earth's?
That's one of my favorite questions. If you go back to that plot, I think it was number 5 in the list that I had. We can show that again for a minute. So we measure the magnetic field around the Earth, and we see all of the sources between us and where it's generated. So it's generated deep inside the Earth at about half the planet's radius. But there's also a contribution to the field that comes from the rocks beneath our feet. Nope, the one right before that. Yeah, and so this plot is the plot that shows you the contributions to the field based on the scale size of that contribution. So the large scale things are on the left, small scale features are on the right. The open symbols in this plot, it was long ago recognized, are contributions to the field due to the sort of random assortment of magnets, if you will, a permanent and induced magnetization in iron-bearing rocks beneath your feet. And it's kind of random. So when you look down on the magnetic field, you have to look through this kind of layer of haze, if you will. And you cannot distinguish the small scale features down on the dynamo, because all this other stuff is like a screen between you and what you're trying to look at. So in spite of all of the orbiting spacecraft and measurements we make of the magnetic field about the Earth, we'll never be able to see the smallest spatial scales of the field down where the dynamo is generated, because there's all this other stuff in the way. One of the advantages to doing your dynamo work at Jupiter is that there is no crust. There are no iron-bearing rocks beneath the spacecraft and the dynamo. And in fact, the dynamo is at a much larger radius, so it's easier to project the field down to that surface to see what it looks like. So that's why we say we already have a picture of a dynamo that is more clear than we'll likely ever have by studying the Earth. And as time goes on, we'll get more and more clarity as we fill in even more orbits. So that's why we're very excited about the extended mission. The story just keeps getting better and better.
We have one final question, and this is from Monica Young at Sky and Telescope. This question is for Leah. If I understood correctly, you concluded that turbulence naturally organizes itself to create a crystal of vortexes at the pole. Does this mean that any giant planet, including exoplanets, might have such vortex arrangements at their pole?
Hey, thanks for this question. So actually, yes and no. So in our study, we identified like 4 basic parameters that may explain the existence of such polar vortex crystal. So it has to do with a combination of the rotation rate of the planet and the radius of the planet, and then how fast the flow goes around the planet, and then also very important, the forcing. So as Jack said, on Jupiter, let's say it's convection. So that means that if we've got a right combination of those parameters, we may find exoplanets that have such crystal. But then on the other end, you take a planet like Saturn, doesn't have such a vortex crystal combination. So we found some parameters that can explain, but in real life, like physics might get a bit more complex than that to fully understand.
Okay, I think that's our final question, and we're just on the hour here, so I think we're going to wrap up. Thank you to our panelists for sharing all that interesting research, and thanks to all the journalists in the audience for attending this press event and any others that you attended during the meeting. This concludes our final press event of the meeting, and I just want to thank you again for all your participation this week and doing our virtual hybrid press events this year. It's been really nice. And on behalf of ATU and the media relations team, thanks to everyone for all the work that you put into making this such a successful week. If you have any questions or need to follow up with anything from the conference, please don't hesitate to get in touch with us at news@atu.org. And we wish you all safe travels over the next few weeks, and we look forward to working with you again in the new year.